In this example, a sail for a boat is simulated using soft body dynamics. To control the look of the sail, ramps are used to control the goal PP attribute. Springs are then used to add realism to the sail. In the file sail01, I have created a very basic sailboat complete with mast and sail. I want to animate the sail using dynamics. There are several techniques that could be used to animate the sail, but using Maya Cloth would probably provide the best and most realistic results. However, if you do not have Maya Unlimited, you do not have the luxury of accurate cloth simulations. The next best thing is soft body dynamics. I'll start by making the sail into a soft body object. In the soft body option box, there are a few options for how to create the soft body. I like to use the duplicate make copy soft option. The reason for this is that if I need to refer back to the original geometry, it is still there, and the dynamic one can be deleted without worrying about removing the original surface. I always make the non-soft a goal, as even if I don't initially plan on using goals, I like to have the flexibility to simply turn them on or off down the road. Since I will be using soft bodies for this effect, I will set the goal weight to 1. I'll rename the duplicated sail Dyne Sail, and the particles Dyne Sail Particles. A soft body object is simply a piece of geometry that has each of its CVs, or vertices, controlled by the position of a particle. The first thing I want to do is add some gravity to the sail. Even though the sail's motion will be billowing out, it still needs gravity to give it a sense of mass and cause it to sag when the wind isn't blowing. It is important to set the correct gravity value. Since gravity is calculated in meters per second squared, regardless of which units you are using in Maya, the default value of 9.8 assumes that 1 unit in your scene is the equivalent of 1 meter. However, since we don't tend to model this way, we need to find the equivalent of 1 meter in the current units and then multiply that by 9.8 to determine the correct gravity setting. I'll assume that the mast of the boat is 3 meters high, so if I measure roughly 1/3 of the height of the mast, I will know that the equivalent is 1 meter. To do this, I'll use the distance tool. The measurement is roughly 2.5, so I'll multiply the gravity setting of 9.8 by 2.5 to get 24.5. When I play back the scene, nothing happens. This is because the particles all have a goal PP, or per particle, of 1. I need to control the goal weights of the particles so that the particles at the top of the mast stick to the mast, and the particles at the bottom stick to the bottom. There are several ways to set the goal PP for the particles. I could simply select the particles in component mode and in the component editor, set their goal PP to 0. The particles now fall. To make the sail blow, I'll use an airfield and set its direction to blow in the z-axis. I could use a uniform field or gravity field pointing in the desired axis, but the airfield offers many niceties that the other fields don't have. To illustrate some of the differences, I'll create a uniform field and make it blow in the z-axis. As the particles fall, they also move in the z-axis. However, if I group the boat, sail, and mast, and parent the field under the group, when I rotate the boat, the field continues to point in world space z-axis. In order to always aim the uniform field in the right direction, I'd have to write an expression to adjust its direction based on which way the boat is pointing. Another key difference between the uniform field and the airfield, which won't really be illustrated in this sailboat example, is that the uniform field provides a constant force in the given direction, so your object will constantly accelerate. The airfield, on the other hand, will apply a constant speed, so if your particle begins to exceed that speed, the airfield will apply less force to it. This is much more realistic when creating an effect like wind, which is a constant speed, not a force. An object that is moving in 40-knot winds cannot exceed 40 knots. I'll delete the uniform field and create an air field. I'll set the magnitude to 20, attenuation to 0. I'll turn off Use Max Distance, set the direction to 1 in the Z-axis, set the speed to 1, spread to 1, and inherit rotation on. Now, when I parent the airfield under the group, its force now rotates correctly. Notice how the soft body is now moving in the x-axis. On a side note, don't confuse speed with magnitude on the airfield. Speed is simply a percentage of the magnitude and operates in the range of 0 to 1. If I set the speed to 1000, it makes no difference. However, if I set it to 0.5, it halves the force. So now we have the soft body reacting to forces. Obviously, this simulation is not what we want. The sail stretches way too much. Since the sail of a boat does not stretch very much and soft bodies always stretch, we need to use some different techniques to minimize this stretching. The first technique is to adjust the goal weights. Goal weights allow you to have the object move with dynamics but in a controlled manner. The lower the goal weight, the more dynamics take over. If I select the particles again and set their goal weight to 0.3, the sail stretches less, but the stretching looks rigid, not at all like the arc of a sail. So we could go in row by row and adjust the weights of each particle to create a nice fall off, but this would be very time consuming. A better approach is to use a ramp to control the goal weights. Since the soft body was created from a NURB surface, the particles are ordered based on the CVs of the surface. I'll set the particle render type to numeric and have it display the particle ID. You can see that the particles are ordered from left to right. So if you look at their IDs vertically, there is a difference of 11 between each of the rows. This means there are 11 particles per row. I'm going to assign a ramp to goal PP. However, instead of using the particle's age as the input to the ramp, I'm going to use the goal VPP attribute. By default, whenever an attribute is created, Maya also creates a VPP version of that attribute as a convenience for hooking up ramps to. I want to control the goal VPP based on some parameters that I define. Since I can see that there is an order to the particle's IDs, I can write an expression to drive the goal VPP based on the particle ID. In the runtime expression, I can calculate a new value for goal VPP by using some of the information that I know about the particles. For example, I know that the difference between one row of particles and the particles immediately below them is 11. Therefore, there are 11 particles per row, or 11 columns. So I can therefore declare that float $number of columns equals 11. If I wanted to have the ramp control the goal weight from left to right, I would write float $u equals ID percent $number of columns. Goal VPP equals $u. The percent symbol returns the remainder of a division. So for example, we know that 4 divided by 2 equals 2. So therefore, 4% 2 would equal 0 since there's no remainder. However, we know that 2 goes into 5 twice, but there is a value of 1 left over, so 5% 2 would equal 1. I'll set the numeric display to goal VPP. The values displayed now go from 0 to 10, from left to right. This means that the particle on the left divided into 11 with nothing left over. The one to the right of it divided into 11 but had 1 left over, and so on. When I play back the simulation, only the first row of particles now moves. This is because the values we are assigning goal VPP are in the range of 0 to 10 instead of 0 to 1, which is what the value of a ramp is looking for. To correct this, we simply divide the results of float u by 10, since we know that 10 divided by 10 equals 1. Why do we divide by 10 and not 11, which is the number of columns? because the first value in every row is already 0, and although there are 11 particles, we are counting from 0 to 10, not 1 to 11. Therefore, I can write float $u equals ID percent dollar number of columns divided by the number of columns minus 1, which would give me a value of 10. Now, when I play back the simulation, you can see that the ramp appears to be spreading its values from left to right. I can now adjust the ramp to intuitively adjust the goal PP attribute and always get nice interpolation between values. With this technique, I can control the sides of the surface, making the surface appear to stick at the sides by making the ramp white at the ends. This would look correct if my sail was connected to the mast at the sides. However, the sail is connected to the mast at the top and along the bottom edge, so I need to have the ramp run from top to bottom. To get the value range running from top to bottom, I'll write float $number of rows equals count divided by number of columns float $v equals the integer of ID divided by number of columns divided by number of rows minus 1. Goal VPP equals $v. On playback, the ramp now affects the particles from top to bottom. Again, I can adjust the ramp until it conforms to the shape that I want for the particles. To stop the particles from bouncing around so much, I'll lower the conserve to 0.925. Let's take a look at the expression I just added and reverse engineer it. I'll start by turning the numeric display back on. Next, I'll comment out the declaration of $v and declare it with a value of ID divided by number of columns. You can see that each row of particles from top to bottom has the same value to the left of the decimal, but they all have slightly different values moving from left to right. We only want to take the value to the left of the decimal. I could use the truncate function to get rid of everything to the left of the decimal, but an easier method is to simply change the value from a float to an integer, which I can do by placing an int before the value. When changing a float value to an integer value, Maya does not automatically round up or round down the value. It simply truncates everything to the right of the decimal place. Now each column of the row has the same value. And then we simply want to get the range going from top to bottom from 0 to 1 instead of 0 to number of rows. So we divide by the number of columns minus 1, since as you recall, we start counting from 0, not 1. These two methods for getting U and V values for particles on NURB surfaces are excellent ways for controlling ramps and creating soft body effects based on surfaces. This technique will also work for polygonal primitives since their vertices are ordered intuitively. A good way of testing whether this technique will work for your surface is to simply display the particle ID number of the soft body particles and look for a pattern that matches the UV layout that you need. Now that the sail is blowing, we want to add some more realism to it. There is currently no relationship between each particle in the sail. If the sail were to be hit with wind in just one area, the particles in the other area would not receive any of the force and the sail would not look very realistic. To create the relationship between particles and spread their forces, we use springs. I'll start by creating some springs with a wireframe walk length of 1, and a stiffness of 100, and a damping of 1. With a walk length of 1, a spring is created between each particle and its neighbor on all sides, but not diagonal to it. This creates a good box type of lattice work along the surface, which provides for very stable simulation. If the particles are connected to too many springs at once, setting high stiffness or damping values can often cause instability. This method allows for a minimal amount of springs per particle, allowing you to use a high stiffness and damping value, which will in turn prevent a lot of stretching. To add some more detail in the way that the forces flow between particles, I'll add a second set of spring objects with a wire walk length of 2 and a stiffness setting of 25 and a damping of 0.5. Remember to always create your springs in the rest position of your soft body, as the springs will remember the length at which they were created and try to maintain it. This creates springs on all sides of the particles, including along the diagonal. This gives the surface more rigidity, even though we are using a lower stiffness and damping value, since the bulk of the stiffness is coming from the first spring object. Depending on how you set up your springs, your wire walk length, min-max settings, etc., you can create different structures to your surface. In the case of a sail, the way that the material is stitched together has a great deal of influence over its shape. Let's say that I wanted to make this sail have more horizontal rigidity so that it had some more billows in it. I would start by creating a new spring object with a wire walk length of 1. I would then select each of the vertical rows of springs in component mode and simply delete them. When going into component mode, it is best to toggle off all components and then simply turn on springs. This will make spring selection much easier. The surface now appears to be more taut horizontally. I can then adjust the stiffness of this spring object to control the tautness of the surface. To add some more realism to this scene, I'll create a turbulence field and animate it, translating in Z to simulate some turbulence in the air. In this chapter, the concepts you want to take away with you are how to use the particle ID and percent function to control the values of a soft body with ramps. I used ramps to control the goal PP attribute, but I could have also used ramps to control the mass of the particles along a surface. By using ramps, you have much more control over how the values are set across a surface. Another key concept is how to layer springs to derive more control. Soft bodies will always stretch, and simply setting the stiffness and damping to large numbers tends to add instability to the simulation. By adjusting the goal weights of your particles, the conserve attribute for the overall particle object, and by layering springs and strategically placing them where they are needed, you can better control your simulations. In this chapter, I'm going to use the particle instancer in conjunction with goals to create shingles for a shack. Using a technique similar to the one used in the BlowingSail chapter, I will lay down the shingles based on the UVs of the roof. In the file shingle01, I've created a very basic shack. At the origin, I created a single shingle that is 1 unit in size. Whenever I work with instances, I like to make the size of the instant object 1 unit so that when I control the scaling of the instance in my particle expressions, I know that a scaling of 1 is 1 unit in the scene. I'll start by picking 1/2 of the roof and emitting particles from it. In the Emit from Object options window, I'm going to set the emitter type to surface, set the rate to 1000, and turn on Need Parent UV. The geometry that I'll be emitting from is a NURB surface, and the emitter will be able to pass the UV coordinate at which the particle is emitted from to the parent U and parent V attributes of the particle. Unfortunately, Maya does not support polygonal UVs when emitting from a polygonal surface. Since I had the Need Parent UV option turned on when I created the emitter, The parent U and parent V attributes were automatically added to my particles when they were created. If your particles do not have the parent UV attributes, you can add them using the Add Attributes window and selecting them from the Particles tab. On playback, the particles emit in the direction of the normals of the surface. The normal information of the surface where the particle was emitted from is very important when trying to orient an instance to the surface of an object. I'll set the max count on my particles to 20 for now, and instance the shingle geometry to the particles. You can see that the particles now have the shingle geometry attached to them. I can control the rotation and scaling of the geometry using the original shingle and have the instance shingles update. However, I want to control each of the shingles' rotation and scale on a per particle basis. To do this, I'm going to open the Attributes editor for the shingles and then open the Instancer section. In this section, I can control various attributes of my instance geometry on a per particle basis, namely the position, shear, scale, rotation, and visibility. As you can see, the position of the instance geometry is being controlled by the world position of the particles. I want to orient the instance geometry to the normal of the surface from which it was emitted from. In the rotation options, I can either control the rotation of the instances directly, or I can aim the instances in a given direction, just as if I was using an aim constraint. Since I know that the particles are emitting in the direction of the surface normals, I can use the velocity of the particles as the aim direction. Now the particles are oriented in the direction of the velocity. I'll add a gravity field with a magnitude of 1 to illustrate this a little bit better. Notice how the instances are initially oriented to the surface. However, as they fall with gravity, they begin to rotate downwards. Since the shingles need to stick to the roof, I'll make the roof a goal object for the particles. The particles now goal to each of the CVs of the surface. They also lose their orientation with the surface. Since we were using the velocity of the particles as their aim direction, and the particles are now goaled to the surface, hence they are not moving, the aim direction is 0, meaning that we have lost our relationship to the normals of the surface. I want to store the velocity of the particles when they are first born, before they are affected by the forces or goals. To do this, I'll add an attribute called normalPP and make it a vector per particle array. In the creation expression for the particles, I'll initialize normalPP with velocity. Now velocity is stored for each particle in the normalPP attribute. I can now set the aim direction of the instancer to normalPP, and when I rewind the animation, you'll see that the particles are now oriented correctly, even though they are goaled to the surface. Next, I want to scale the shingles so that they are a little bit more realistic in size. Since I am not controlling the scale of the instances with a particle attribute, I can simply select the original shingle and adjust its scale. Later on, when I am controlling the scale with a per particle attribute, I'll have to set the scaling back to 1. Notice that even if I rotate the original geometry, the instances no longer rotate, since the rotation is now being controlled by the normalPP attribute. The instances are now the right scale and size, so it's time to place them on the roof. Currently, the placement of the shingles is being controlled automatically. Each particle is goaled to a CV on the surface. Since I want precise control over the placement, I'll need to add goal U and goal V attributes to the particles so that I can place them in UV space over the goal object. I want to set up some higher level controls to control the number of rows and columns of shingles on the roof. I'll create an empty group node and name it Shingle Setup. To this node, I'll add two attributes, columns and rows. And I'll set their initial values to 5 and 6. In the channel control window, I'll hide the translate, rotate, and scale attributes so that they don't show up in the channel box. However, before hiding them, I'll lock them so that I don't accidentally transform this node. In the runtime expression for the particles, I'm going to add the following expression. As I play back the animation, I can adjust the number of columns interactively, since the runtime expression gets evaluated each frame. Let's take a look at the expression I added. I first capture the particle ID, which is unique to each particle. Next, I declare variables for the number of rows and columns. I declare the variables as float and not int variables, since I will be using them to divide other values. In Mel, when you divide a value by an integer, the result is always an integer. This often causes problems in expressions where you need fractional numbers but only get whole numbers. For goal U, I am setting a similar function to that of the BlowingSail example. First, I take the ID of the current particle and get its remainder based on the number of columns. So if the ID was 8 and the number of columns 5, it would return a value of 3, since 5 goes into 8 once, but has 3 left over. I then take the remainder and divide it by the number of columns minus 1. Rather than showing the mathematical proof as to why I subtract 1, simply take out the negative 1 and see the difference for yourself. Instead of the particles centering themselves from edge to edge, they are aligned to the left. Most of us are not mathematicians that can visualize the results of an equation simply by looking at it. Runtime expressions are a great way for you to visualize your equations quickly, changing them around and seeing the results visually. I'll hit the undo key to undo the changes I made to the expression. Next, I want to control the number of rows of shingles. I'll add the following line to the expression. If you recall from the BlowingSail chapter, this is the exact same expression that I used to create the UVs for the soft body surface. On playback, you can see that the particles now form rows and columns, but the rows are not reaching the top of the roof, and they seem to be randomly spaced. This is in part because I set the max count of the particles to 20, yet I have specified that I want 5 columns and 6 rows, which would be 5 by 6, or 30 particles. I'll set the max count to 30, and now the particles fill the roof, but the shingles are still not ordering themselves correctly. This entire expression relies on getting proper particle ID numbers for each particle, which unfortunately doesn't seem to always work correctly. Unlike a soft body object which has a constant number of particles with a clean ordering of IDs, when particles are emitted in Maya, new IDs are constantly being generated. Usually, IDs are generated with a unique integer, and usually in the order of 0, 1, 2, 3, etc. However, sometimes Maya's ID numbers are not integers and are instead float values, and you end up with some particles that are ordered correctly and some that may be ordered, such as 35, 36.4, 36.8, 38, 41, 42, etc. Each ID is greater than the last, but it's not necessarily greater than the last by a clean value of 1. What I'm about to show you is a very important tip when working with particles. In this example, we know that the number of particles that we want is simply the number of rows multiplied by the number of columns. So in an expression I can type particle1.maxCount is equal to shinglesetup.rows times shinglesetup.columns. I'll set the render type for the particles to numeric and display the particle ID. You can see that some of the particle IDs are actually decimal values, not integers. For efficiency, once Maya emits a new unique ID, it remembers it and reuses it the next time. So from now on, some particles will have proper integer-based IDs, and some will have floating point IDs. This wreaks havoc on expressions that base their equations on each particle having an integer value for its ID, and that the previous particle's ID is 1 less than the current particle, and that the next particle's ID is 1 more than the current particle. I believe this stems from the fact that the max count attribute was adjusted while there were currently particles on the screen, and somehow this messes up the ID system. Regardless of how it occurs, it can quickly corrupt a simulation. A unique ID is not as important in this expression as a continuous ID stream. So what I'm going to do is show you a technique for generating your own IDs for your particles during their runtime expression. I'll add the following lines to the top of the runtime expression. And at the end of the expression, I'll add in the beginning of the expression, I initialize an integer called particle ID. I then set the ID variable that I created earlier with its value. And at the end of the expression, I increment and test to see if its value is greater than or equal to the max count. The runtime expression gets run for each particle in order. So as each particle evaluates the expression, the ID increments. When we reach the last particle, which we know because we know the max count, and we know how many we've iterated through since we have been incrementing particle ID, we restart the counter. Now, each particle has a unique integer value that is properly ordered, regardless of what Maya thinks the internal ID to be. By adding a simple print statement, you can see that the resulting ID that this expression creates is more sensible than Maya's internal ID. If I set the number of columns to 10 and number of rows to 15 and rewind the simulation, I get a nice distribution of shingles. When I lower the number of columns to 2, the shingles adjust themselves on the surface correctly. However, where once I had 10 by 15 shingles, or 150 shingles spread out evenly, I now have the same number of shingles all clumped together in 2 rows. You can see in the script editor that the Maya ID is usually an integer value, but occasionally it produces a floating point value, which would throw off the position of the shingles. However, the custom ID that I created is always an integer and provides for smooth placement of the shingles. In the attribute editor, the count of the particles is 150, but the max count is 30. That means that there are an extra 120 shingles in the scene. When the scene is rewound, this problem goes away as the max count kicks in and only 2 by 15 or 30 particles are emitted. The file shingles02 contains a scene up to this point with some renaming and organization of the nodes. You can continue with your file if you like. I'll add a few more controls to the shingles to show what the benefits are of building a roof out of instance geometry. I will add some variation to the size and orientation of the shingles. First, I'll set the number of columns to 20 and the number of rows to 15 so that we get a good amount of shingles on the roof. I'll add an attribute called scalePP as a vector per particle attribute, and an attribute called birthNormalPP also as a vector per particle attribute. I'll add the following control attributes to the shingle setup node: shingle scale as a vector attribute, and shingle age as a float attribute. I'll set shingle scale to 0.3, 0.1, and 0.25, and shingle age to 0.2. When I rewind the simulation, the instances disappear. When I added the scalePP attribute to the particles, Maya automatically set the instancer to use scalePP to control the instance's scale on a per particle basis. This behavior is not documented, so be careful when adding attributes with names like scale or rotate PP, as you never know when the instancer might start using it. For now, I'll set the scale back to none. As a roof ages, it begins to sag and the shingles start to fall out of alignment. To simulate this aging, I'll adjust the scale of the shingles and their orientation based on the age. In the creation expression for the particles, I'll assign birth normal with velocity, so in essence I am simply storing the normal at birth. To add some randomness to the size of the shingles, I'll use the sfran function, which will add randomness in all three axes. The values that get called by the sfran function are based on a radius for a sphere from within the function will get its random numbers. I'll do the same thing to the normal pp of the shingles and add some randomness in all three axes to the stored normal, birth normal pp. In the instancer settings, I'll set the scale to get its values from scale pp. When I rewind the animation, the shingles now all have a slightly randomized size and slightly randomized orientation. However, since I'm assigning randomness on each frame, when I play back the animation, the shingles are constantly scaling and rotating. Since I want each shingle to preserve its random position, I can simply assign the random seed generator a constant value for each particle. In the expression editor, before the two calls to the sfran function are called, I add the line seed $ID. On playback, you can see that each of the shingles preserve its randomness from frame to frame and they are no longer popping. You could take the aging concept a step further and slightly offset the goal U and goal V with some randomness as well, or even cycle through some different instances of shingles, each getting progressively more worn and deformed. This example of tweaking the scale and orientation is really just the tip of the iceberg in terms of the type of controls you can have over a large number of instances. One last example of the benefit of building objects out of instance particles is that at the end of the day, they are all dynamic. I'm going to simulate a tornado tearing through the shack, pulling off the shingles as it goes by. Open the file shingles03.ma. This file has some of the nodes organized under the Shingle Setup group node to allow for easy scaling of the effect, as well as easy hiding and unhiding of the shack. I'll select the particles and add a volume axis field. I'll set the magnitude to 5, away from axis to -20, along axis to 8, and around axis to 3. Next, I'll scale up the field and animate it moving across the shack. When I play back the animation, nothing happens. This is because the particles have a goal PP of 1, which means they follow their goal 100%. What I need to do is figure out a way to have the shingles release their goal when the force is strong enough to pull them off the roof. All fields attach themselves to the input force of the particle shape. If I open the hypergraph for the particle shape, you'll see that the volume axis field is connected to input force 2 of the particle. I can access the amount of force being applied from each field through my runtime expression. At the end of my runtime expression, I'll add the line, if the magnitude of input force 2, which is the volume axis field in this case, is greater than 3, then set the goal PP to 0. This line simply states that if the magnitude of the input force of the field attached to element 2 is greater than 3, then you should turn off the goals. When I play back the animation, as the field passes over the particles, it begins to pull them off of the roof. This is a great technique for having per particle control over the effects of any of the forces in your scene. The use of particle instances for creating geometry is a powerful way of building your environment. The instance geometry is quite memory efficient in that only the original geometry and the particles are stored in memory, so you can create thousands of instanced objects with a very small memory footprint. While you could write an expression for each instance, the runtime and creation expressions of the particle system is much more robust. You could design a particle expression that would generate an entire building complete with bricks, mortar, and windows with a single particle object, and then destroy the building by simply adding some fields to it. The other important technique that I showed you in this example is how to read the input force information on a per field and per particle basis. If, for example, you wanted some particles to be affected by an attached field and not others, you could simply invert the input force of that field and apply it to the velocity of the particles, thereby nullifying its effect. Or, if you were creating a tornado simulation and you didn't want your particles to spin out of control, you could dial in and out a varying amount of the attached vortex field by subtracting a fraction of its force from your particle object's velocity based on how quickly your particle is currently moving. The hardware render buffer uses the graphics card in your machine to render images. The images are drawn to the screen using OpenGL, similar to the way that Maya draws the screen in your viewport. However, the hardware render buffer goes much further than that. Using a buffering technique, it can render multiple snapshots of your scene and then layer them together in a process called multi-pass rendering. This enables it to perform functions like motion blur, where the image is rendered at different times, stored, and then layered together to simulate time-based blurring. Another feature of multi-pass rendering is that it can be used to jitter certain types of particles to create a softer-looking particle. Open the file fire02.ma. There are two particle render types that can take advantage of the jittering that occurs during multi-pass rendering, multi-points and multi-streaks. In the file that I just opened, the fire particles are currently set to multi-points. A particle is just a position in space. How that position in space is represented is dictated by the particle render type you choose. A multi-point render type is simply a collection of points centered randomly around the position of the particle. The number of points is set using the multi-count attribute, and the distance away from the particle that the points are drawn is controlled by the multi-radius. During hardware rendering, when you turn on multi-pass rendering, during each pass the hardware render buffer will draw those points in a slightly different position, but within the same multi-radius value away from the position of the particle. I'll make sure multi-pass rendering is turned off and test render the scene. Sometimes, when test rendering, the image disappears immediately after it is drawn to the screen. This usually occurs if the particles are selected or you have motion blur turned on. By deselecting the particles, this refresh issue usually goes away. If it doesn't, sometimes rendering the same image 2 or 3 times will make it stick. Otherwise, set the start and end frame in the hardware render globals to be the current frame and render the sequence and then view it in fcheck. Notice how the particles look the same as they do in the Maya viewport. I'll turn on multi-pass and set the number of passes to 5. Now, when I render the image, you can see that the particles are drawn 5 times, and each time the position of the multi-points shifts slightly. The resulting particles look much softer. By adjusting the number of passes, size of the points, multi-count, and multi-radius attributes, you can achieve very different looks for your particles, ranging from fine mist to thick cloud. Factor in opacity values and you have a ton of control over the look of your particles. Another important factor in defining the look of your particles is in the motion blur settings that you use. Particles tend to be very small and move over very large distances relative to their size. This results in quite a lot of motion blur. A tornado, for example, is primarily made up of billions of tiny dust and sand particles, blades of grass, leaves, as well as larger debris like trees, cars, barns, and the odd cow or two. However, when viewing footage of tornadoes on TV, they are all moving so quickly that they seem to merge into one blurred mass. Before I start testing the motion blur values, I need to cache my particles. Anytime you are going to render your particles, you should first cache them. However, when I am testing the rendered look, I usually like to do so without having the particles cached, as I often need to go into my particle object and adjust the motion slightly, or parts of the particle expressions for opacity pp or RGB pp. Caching stores all of the values for attributes that are either controlled by expressions or affected by fields. Attributes that are controlled directly by ramps can usually be adjusted even after the particles are cached, as you'll see once I finish caching the particles. The reason why I say usually and not always is that usually when you apply a ramp to an attribute, the particle's age is used to control the position in the ramp. Since age is cached, the actual value of the ramp does not need to be stored, as it can be calculated in real time quite efficiently. As I showed you in the chapters on dust and explosions, you can control the position of the ramp that is being sampled through expressions. For example, in this scene, the RGB PP is controlled by a ramp, and even though the particles are cached, I will still be able to adjust the values of the ramp and see the updates on my particles. Once I am happy with all of the particle attributes, I then cache the particles and tweak the motion blur settings. The reason that you must have your particles cached before tweaking motion blur settings is that during the motion blurring of the image, Maya changes time, and each time that time changes, the particles reevaluate themselves. To cache the particles, I simply set my time range to the desired cache range and open the Particle Render Cache Options window. It is recommended that you set the cache directory name to the name of your scene. Although Maya should be able to use any name for your cache that you choose, you will often find that if the cache name is not the same as the scene name, when you reload the scene, the cache will not work. Sometimes it does, sometimes it doesn't. It's buggy, so I recommend sticking to the scene name. If you need to have multiple versions of your cache files, create multiple copies of your scenes and name them accordingly. If the cache directory doesn't exist, Maya will create it and place it wherever your current project's particle directory is set to. If the project does not have the particle directory assigned, it is also automatically created. As Maya caches the particles to disk, you'll notice that inside the particles directory of the current project, a subdirectory is created called Fire02. Inside this directory, files are being written out. For each particle object in your scene, a separate file will be created per frame. The frame numbers and the file names do have a relationship. Simply divide the file number extension by 200 to determine which frame that file is for. The reason for using a value of 200 is that Maya supports oversampling of up to 200 times per frame. So, if you set your oversampling to 2, the resulting frame numbers would be 200, 300, 400, 500, indicating frame 1, 1.5, 2, 2.5, etc. A very important thing to remember when caching your particles is that if you have duplicate particle names in your scene, they will overwrite each other's caches. You can often duplicate particle names in your scene if you import an effect that has a parent node above the particle object. Maya will rename the parent node, but will not rename the child nodes, as it will refer to the child by its long name, parent, pipe, particle name. However, when writing the particles to disk, it does not use the long name. Now that the particles are cached, notice how I can still adjust the values of the ramp and have the results shown on my particles. I can start to adjust the motion blur settings as well. When Maya motion blurs in hardware, it simply takes a specified number of snapshots or samples over the specified motion blur range. So, if you have 5 render passes set and a motion blur of 1, Maya will step forward through the frame in increments of 0.2. A high motion blur value combined with a low number of passes will often result in a final image that looks stepped. Increasing the number of passes will smooth out the motion blur. I'll set the motion blur to 1 and use 7 render passes. With these settings, the multi-point particles appear slightly blurred, but they are not coming together to form continuous flames as a real fire would. I'm going to change the render type of the particles to multi-streaks. Multi-streak particles are another OpenGL type of rendering for particles. Basically, a streak particle is a line whose length and orientation is controlled by the velocity of the particle. The streak can be tapered at either end, which results in a streaked type of look without the use of motion blur. As with multi-points, multi-streaks are a group of streaks offset from the position of the particle. When I select multi-streaks, the particles disappear. This is a normal behavior for the multi-streaks, as they do not initially know what their velocity is, so they assume that it is 0, which means that they have a length of 0 and therefore they are not drawn. Normally, when you step forward to the next frame, they are drawn correctly. However, since we cached our particles with a render type of multi-points, Maya by default does not cache velocity, as it knows the position of the particles, so it really doesn't need to keep the velocity information. But if I had set the particle render type to multi-streaks before caching, Maya would have known to cache the velocity of the particles, since that data is required for that render type. Therefore, I need to recache the particles to have the streaks show up correctly. Now that the particles are cached again, you can see the multi-streaks are now beginning to draw correctly. I can now adjust some of the multi-streak parameters to get a better look for my fire. Tail length acts as a multiplier of the velocity of the particles, so a particle may be moving very slowly, but if you have a high value for its tail length, the tail will be disproportionately long. The width of the streak also can be adjusted, as can the amount of tapering that occurs using the tail fade attribute. You can see that without any motion blur settings, the fire already has a blurred look to it from the tails of the streaks. With a little bit of motion blur and some tweaks of the parameters, I can get the particles to look a lot more like fire using this render type. Once again, I have added several more parameters to my simulation that affect the final look. Different render types, different multi-counts, multi-radius, point size, tail length, number of passes, and motion blur values all affect the final look of the particles. Assuming that this is the final look of the fire, I can now render the sequence. The hardware render attributes window is similar to the render globals window. However, it is important to remember that the two are completely separate and share none of the same values. This means that if you have set your resolution and file naming conventions in the render globals window, you have not set them in the hardware render globals, and your images will not be rendered with your settings. Setting the file name, extension, frame range, and image type are all pretty straightforward. The resolution, however, is not as intuitive. If the resolution that you would like to render at is not in the list of default resolutions, you can manually type it in. The format for this resolution is name of resolution, resolution in X, Y, and aspect ratio. So in our case, I'll call it DVD, and then I'll put in 720 for the width, 480 for the height, and an aspect ratio of 1.5. The aspect ratio can be anything you like. However, if you use a non-square aspect ratio, your image will be rendered using non-square pixels, as it would with software rendering. So a square aspect ratio for 720 by 480 would be 720 divided by 480, which is 1.5. An easy way of determining aspect ratio is to open the Render Globals window and enter your resolution in it. It will automatically fill in the aspect ratio for you. Alpha source is a cause of much frustration. Some video cards support hardware-based alpha channels, others don't. Those that do usually don't render out proper alpha channels for particles, but do render out proper alpha channels for geometry. When particles are drawn in the viewport in Maya, the alpha channel is properly calculated, which is why they properly occlude objects behind them. However, when rendered in Compt, the alpha channel is usually incorrect, which makes achieving the rendered look inside the Maya viewport impossible in the final compositing stage. The reason for this is that when the particles are drawn to the screen, the alpha value of the particles add up in the same way that color accumulation causes the RGB values to add up as one particle is drawn on top of another in depth. However, in the hardware render buffer, the alpha channel that is written to disk is not necessarily the accumulated alpha value. It seems to simply instead take the final alpha value that was drawn to the screen and use that. Using luminance for the alpha channel is simply wrong, as it flattens the image. By using luminance, you are taking any area that has shading information in it, whether it be in the texture map of a sprite or in the accumulation of colors creating hotspots, and saying that where there is shading, the image is more transparent. So a thick, oily smoke would end up being completely transparent in the alpha channel, as it would mostly be black. Clamp and inverse clamp can be somewhat useful, but they simply look at the image, and if there is any value for the pixel that is greater than 0, it makes the alpha channel 100% solid. So, if you have any opacity value less than 1 on your particles, the resulting alpha channel will be completely white, instead of a shade of white. Red, green, and blue are the most usable channels. If your particles have no color information, for example smoke, Or if you plan on coloring them in the compositing stage and merely need some shading information on them, then you can make the background color of the hardware render buffer display either 100% red, green, or blue, and set the alpha to be the background color. The resulting alpha channel will now properly represent how much of the background is showing through. This technique works best if the background color that you are using is not being used by the particles that are being drawn. If it is, the resulting alpha channel will cause the image to appear flat, similar to how luminance takes away any shading information in the image. This can be corrected in your compositing software using various keyers such as PriMatte or Ultimatte, but there's an easier technique to correcting this. You need to render 2 render passes for your particles, one for color and one for alpha. To do this, I first render the cached particle sequence with no alpha channel set. Next, I select the particle object and delete its RGB-PP attribute. If RGB-PP is driven by an expression, I simply comment out the expression in the expression editor. If it is driven by a ramp, I disconnect the ramp. The particles are cached. Any changes that I make to the expressions or connected ramps and fields will not affect the particles. But what does affect the way particles are drawn are the attributes that Maya uses internally to draw them. When Maya draws particles to the screen, it checks to see if an RGB-PP attribute is present, and if it is, it uses that attribute for the color of the particles. If the attribute is not present, and the particle has color R, G, and B attributes, it uses those. Otherwise, it uses the color of the shader that is assigned to the particles. I'll add RGB per object color to the particles and set their value to 1. Now the particles that are being drawn to the screen have a value of 1. If I set the background to black, the particles now show varying amounts of the background behind them, depending on what their opacity is set to. When I render the image sequence now, the color channel can be used as the alpha channel for the image. So I can either set that up in the compositing software, or I can set the alpha channel to luminance, as in this case, luminance is correct. The Z-depth channel only works for geometry. Unless you are instancing geometry to your particles or using the sphere render type, your particles will not register a Z-depth value in the Z channel. While this may seem frustrating, it makes perfect sense. For the most part, particle simulations that contain opacity levels of less than 1 should not have a Z-depth value. Since the opacity is less than 1, the particles are most likely being used in some sort of volumetric effect. And since a volume has many depths, at what point do you choose to specify the Z-depth? The render modes for the hardware render globals don't need much explaining. A couple of things to remember are that if you are using sprites, you need to have texturing turned on. Always turn on line smoothing, as you never want jagged, stepped lines. Always turn on full image resolution, as this way if Maya needs to tile the image because your resolution is set to a value higher than the hardware render buffer can support, your image will get rendered in tiles and then seamlessly put together. In the file Geometry Mask 01, I have a sphere moving through a cloud of smoke. I first software render the sphere. I then open the hardware render buffer and turn on Geometry Mask. When I render a frame, you can see the cutout of the sphere and the smoke. When I comp the particles, the smoke will layer correctly on top of the sphere without the need for any Z-depth compositing, assuming that I have proper alpha channel values set. A few things to remember about geometry masks. If your geometry has a shader assigned that has any transparency, it will not show up correctly. If I set the transparency for the Lambert shader to a value greater than 0, you can see that the geometry now shows up in the render, even though geometry mask is on. A good rule of thumb is to assign a new shader to all of your geometry in your scene. That way you can ensure that no objects end up popping up in the render because their materials might have a little bit of transparency. Your display resolution counts when rendering in the hardware render buffer. This means that if you have your display resolution set to 1 for your NURB surface, it will appear tessellated when hardware rendered. The best thing to do for each NURB surface in your scene is to turn on its display render tessellation flag. That way the cutout of the object will better match the software rendered geometry.